so let's continue on the lecture. We'll start on chapter 11. Chapter 11 and chapter 12 is about aromatic compound. So first, this chapter introduces the aromaticity, and you will see the spectral stability of benzene. And it's kind of a continuation with the conjugated dienes and conjugated trienes, but it's very special because it becomes so stable. So in some sense, you have those conjugation similar, but it becomes like some kind of like a qualitative change. So far we see those in the last few chapters is about sort of the aliphatic hydrocarbons. Now this chapter we're going to begin to see those aromatic compounds. We call them arenes. Arenes are hydrocarbons based on benzene ring as a structural unit. One factor that makes the contribution in arene special is its cyclic structure, cyclic nature. Okay? So when you have the conjugated system that closes on itself, and the property has qualitative change, it becomes so different than those open chain polymers. Okay? And some of those usual reactions that we're having for those one double bond or two double bond will not usually happen for those rings. Example of those arenes is here. One example is benzene, okay? And another one is toluene, and then we have the nomenclature. And we will first study those naming and structure. Then the last section we will study how you identify what compound is aromatic and what compound is not. So benzene is not a cyclohexane triene. Even though in the structure it looks like we have a three double bond, you can call it a triene. A cyclic is not. Okay? It will go through totally different reaction than those alkenes, than those double bonds. Okay? All those atoms, 6H6 carbon on one plane, and all the carbons are sp2 hybridized. And this structure here show you the broad stick model show you the bond angles and distance. So all the bonds in the circle between carbon and carbon are the same. There is no difference. So that is one special characteristic. And this stick model only shows those sigma bond. Okay, you can see this. These are the bond here, are the sigma. Only shows the sigma bond. Okay? And here I show you those electrons in the p orbitals. So usually you will show the benzene with those resonance or conjugated structures like this. So you start with one structure, then you can oscillate those double bonds. Okay? And you still have the cyclohexane. Now this time you can shift in the double bond at a different place. see how you go from the how you go from left side to the right side. You can just show something like this. So this electron move into this bond here, and this electron move here, and this electron move there. And vice versa. If you want to see this, how this right go to the left, this two go here, this two go there, and these two go there. So these two structures together, we call that resonance structure. Then sometimes people use the sort of the Robinson and the Kikuo structure. What is that? Is Robinson Kikuo structure or Kikuo symbol? Yeah. The molecular somehow there are too many spaces in that. Yeah. So these two together, the Robinson symbol or the Kikuo structure. The two different names for the same structure. That means you draw a structure like this. You draw a circle inside. Usually we will not use this Robinson symbol. We usually use the resonance structure on the left side. Okay? Because this Robinson symbol can tell you, okay, so you have one circle just goes around, and then you have this other 6 bonds, so that kind of give you a good understanding. All the bonds in the ring have the same length, same strength. But if you think about it in terms of those orbitals, it doesn't make sense. If you think about that one circle is one orbital, then there will be 6 electrons in it, right? Now we know one orbital cannot take 6 electrons, can only take 2 electrons. Right? So that 6 electrons actually they exist as 3 orbitals, and that 3 orbitals will have those kind of structures. Sometimes you will see the orbital there some nodes between 2 carbons. And use those resonance structures for people's better understanding later on when you see those substitution on maintenance, why they will prefer the so-called ortho or meta or parallel positions. And the stability is very, very strong, stabilized. And if you compare this few molecules, 3 molecules here. We have this real molecule, we can have a cyclohexene, and we can have a cyclohexene, and conjugated, and we can have benzene, but that is a hypothetical cyclohexene triene. So according to the hydration energy, and you can hydrate this double bond, you see you can release 120. Some kilojoule per mole, right? And so that if there is no conjugation and only adding another double bond onto that one, you expect that one will release 2040. Right? But because the conjugation stabilized that releases 2031. Right? And similar, so if you take a benzene and if you adding like this 120, you will get 330. 360. Right? So 360, but in reality you get 208. So therefore there's 150 times stable than that hypothetical molecule. Right? And then here I say that this you can estimate how much it will stabilize. Is at about 6 to 10 times stabilized. Those numbers tell you those numbers. For example, if you examine this stable of this one double bond compared with $2 bond, so that the stabilization is because of conjugation. Okay? So you're supposed to get 240, but you only get 231, so therefore you sterilize by 9, by 9. Okay? So 2 double bonds sterilized by 9, that means each double bond sterilized by 4.5. Right? And here, the benzene was sterilized by 150. 150 is about 10 times of 4.5. Yeah, something like that. So 150 or something. You have 3, you have times 3, right? Because each bond, you have 3 bonds there, and each bond sterilized by like 4.5, and then you sterilize by 3 of them, about 15 times 10 to the 150. So those never make sense. So then the physical properties, they are very similar as other hydrocarbons. So they are nonpolar and insoluble in water. They are less dense than water. Okay. So then we will talk about the naming, and if you have the benzene, have the monosubstituted benzene, you just name that as a substitution of benzene. Okay? Let's see. One example is you have this one. I would like to use this resonance structure. So we have a BR here. Okay? And then the name will simply become bromo benzene. Okay, another example, a monosubstituted benzene like this. Okay? And this called the terbutyl benzene. Last example of monosubstituted benzene is you put NO2 here. NO2 is a group of nitrogen. For disubstituted benzene, the location of the substituent can be specified in 2 ways. You can use the letter OMP, or you can spell out also meta and para. Okay? So the also or the O referring to the 1-2 relation. Also, that means 1-2. Okay? Disubstituted, which means you have 2 something on the benzene. Okay? Meta means 1-3, and para means 1-4. And there are some common names for disubstituted benzene. Okay? One good example for the disubstituted benzene is the xylene, the common name. Okay? And so xylene, that means you have 2 methyl on your benzene ring. And you can put 2 methyl here like this. So they are in 1-2 relation. You can call this O xylene. And the IUPAC name is 1-2. One, 2 dimethyl benzene. Okay? So that's another name for this O-xylene. And then you can guess a name for this. So if I give you this 2 methyl on the benzene, they are relatively in 1-3 location. And you can call this M-xylene, right? And you can also call this 1,3 by methyl benzene. so one last one is we still have a methyl, two methyl on benzene. You can put one methyl here, one methyl here. Okay, so this, actually this is 1, 4 dimethyl. Dimethyl benzene. Oh, when you say this, so this is the sort of P xylene. So some of them don't have a common name. You will be examined by those name problems on the quiz or exam. So I'll give 2Cl or maybe like that. And you can call this O dichloro benzene. Because O, then you can use the number. You can say 1, 2. Dichloro benzene. Ready? So you can have different two group on these. So let's see, we have this nitro here, and we have this methyl here. Now this you will see there is a parent. Okay? So some of those common like monosubstituted benzene become so common. We will name something like if there's something else on it, we'll name like starting from that. Right? So in this one, you see this one before, like with one methyl on it, we call that toluene. Toluene here, right? One methyl on benzene, and that becomes so common. Toluene becomes very, very similar as benzene. So therefore, the name will depend on that. Okay, right? So this guy, you can call this is sort of the M nitro toluene. Okay. It's more common than if you call this like one methyl, three nitro benzene. So we don't call that. Okay? So we call that the M nitro toluene. And you can call this 3 nitro toluene. Get it? And another common name for the monosubstituted guy is this. The benzene. And let's see, we have this carbon here. And then we have this C3. This guy by itself is sort of the acetophenone. Acetophenone. Now if I put a fluorine atom at the para position, and you don't name this with something benzene, more acceptable is name this as P fluoro acetophenone. I want to use a number. You want to use a number? Let's see, 4 fluoro acetophenone. So this is O. And so those, as I emphasized before, those names in table 1, 11.1 are acceptable common name in IUPAC. Okay? So therefore, if there are some derivative from them, and you commonly will use them as a parent name, like what we saw in the last two examples. Toluene is the parent, acetophenone is the parent. So you don't go back always to benzene. And table summarize this. So I recommend you to memorize those common names. So this is the first one, benzaldehyde, benzoic acid, styrene, acetophenone, phenol, anisole, aniline. Not too much you can say about the naming, just memory. Let's see, write a structural formula for each of the following compounds. The first one, you want to write. The first one you want to write is O-anisole. And then you go back and see what is anisole. Anisole is right here. Anisole means you have a bending, then you have a methoxide group like this. Anisole. Okay? And when you have those names to start, you're going backward. You're starting from very, very last part. Okay? You first identify the anisole. Okay? Then you identify, you have a O location. So this is O. There are other O there, but doesn't matter which O you use. Okay? And anisole, that means you have two carbon. Okay? Two carbon attached on that. Then that's it. The other one is M-chlorostyrene. Okay? And the styrene is this guy. Styrene. So this is styrene. M-chloro. M location. Also we have 12 that. And you can put one, you can just put one here. So this is M-chloro. And C is p-nitroaniline. Again, you starting from the last part. Aniline means benzene with NH2 on it. So this is our aniline. P means para. Obviously, there's only one location for P. Nitro is NO2. You can write NO2 or O2N, but just emphasize the atom directly bonding to the benzene ring is N. When you have a 3 or more substituent on benzene ring, you don't use OMP anymore. You have to use numbers. Right? And it too comes from aniline. Okay? So this aniline. Aniline is this. Anisole also special. This anisole. This anisole. Not very close, but this is O, okay? And this is C is 3. But you can write same as this. O and like this. These are the same. Okay? This is anisole. The anisole, right? anisole, aniline, and styrene. So those are common names. So if you have something, you just name as starting from that. Then you need to identify if you have this NO2, nitro, and in this location you call that a para. Para are kind of parallel, so that means the opposite. Right. So you can see there are a few examples here. You have 3 salts treated on it, and you don't use M and O, but you still. Sometimes you still like if there's those names, there's a structure, and part of the structure is in the table 11.1, you choose that as parent. Okay? For example, the first one, you see this anisole, you don't have that in the table. You don't have that in the table. Right? So you have this in the table, so the name was anion like with anisole. And then what you do, you make a number. The number this way will give the fluorine a small number. If you need number this way, you still give this S or 4, but you will give that ridiculous large number. Right? So therefore you do this way. Try to get the number as small as possible. It make sense?
Can you say that again? The number?
The number you try to get in the lowest number as possible.
For all of them? Or for each?
Yeah, for all of them. For all of them.
Okay.
You know which one you're starting from. Okay? So if you don't have a choice to starting from, and then you make sure you starting with one, and then you make them all small. But this one you know which one you're starting from. You're not starting from this to make them small, right? You're not starting from this to make them small. You're starting from this to make them small. If you don't have those spectra, you can start from one that make them small. And that's all those then you can, if there's a tie, you can use alphabetical order and so on. Right, and this second one also has something special here. I think the special one is indicated by the blue. Okay? So blue one is special, and this is toluene. Right? And the number, no like ambiguity, you have starting with this one. And 1, 2, 3 going this way, or 1, 2, 3 going that way, the same. Okay? And this one, you see, you have this one also special toluene, that also special aniline, then which one you go with? You go with the one that's like more electronegative. So you go with aniline, right? And yeah, so 1, 2, 3 goes this way. You don't go that way. You go that way, you do this to number 2 way. All right. So if all the salts taken not included in the table, you are starting with one that make the difference. Chlorine, nitro. I think for this first example, you start on the chlorine, and that will make the number smaller. Right? So that's it. I think that, and you can try out a different way. You will see the number will not different. Yeah. How you get a small number?
Yeah, I'll figure out which one's the small number.
For which one? For these two? For the last few?
Sure. Let's do that.
Okay, for this one, as you guess, you know you have the starting from, let's say we have this structure here, then we redraw there, because otherwise for that meaning. Okay. So these are benzene. Then you have this anisole here, you have the fluorine here, you have the ethyl here, right? You number them like this. You know you have the starting from this. Okay? But this guy is our anisole.
40%.
But this anisole has those blue one, the blue OC3, blue C3. They are in the table 11.1. See 11.1 here. You have this one here, the anisole here. That means you have the OC3 on the benzene ring, right? And so therefore, there's other two. There's a fluorine, right? So fluorine here, and ethyl here. But these two is not in the table. You can see. So therefore, it's not. You cannot use those as parent name.
So if the substituent group is in the is one of the ones in the table, that's where we start from.
Yeah, you know for sure. And if there is two, then you have to decide which one you go with.
Which one is more electronegative?
Yeah. Right? Yeah.
Wouldn't you get, if you had a more electronegative one that made it longer, wouldn't you still start at the more electronegative one? Like if you go to the example you just gave.
Yeah. Once you decide that one will be a parent, you may get normally go with that.
No, if you don't have a parent, at all, and say you have a fluorine that's like 2 away from 2 substituents.
2 location away from what?
Like if you go back to the example you were drawing for her, like if the fluorine was where the ethyl is, and there was no parent group, but there was like the ethyl was in the place of another ethyl was in the place of the oxygen. And
okay, so you see you have a structure like this. So you have a fluorine here.
yeah,
You have an ethyl here.
yeah.
You have another ethyl somewhere.
No, you have another ethyl closer to the left side.
To the left side.
Yeah.
Here.
Yeah,
And then.
yeah. Wouldn't you start one at fluorine?
That you want to make the number smaller. Okay? If you start with, let's say, if you start with fluorine, okay? So this is 1, 2, 3, and 4. Okay? And let's say you get 1, 3, and 4. Okay? Now let me start with different atom. If we starting on this ethyl 1. Okay, and 2, and 3, and 4, so I get 1, 2, and 4. Adding together, this gives you 7, this gives you 8. You probably go with the red number. Not that complicated. Although, if I have, you first start with those guys in table 11.1. Right? And then from those I might put one more group on it, and then you know how to use that as parent. Right? So I give you two atom or 2 group atom on benzene, that becomes relatively easy. Right?
So the first example of halogens is the lower number, active one number, you get halogen lowest number.
Halogen is not that much high priority in naming. They never. Fluorine, chlorine, bromine, they never have any like those priorities. You just treat them as H or carbon. So here we see like this red number because we have 1, 2, 4. You altogether get 7. If you use 1, 3, 4, altogether you get 8. So your number is higher. You want to use a small number, that means you want to use a small number. You already know you start with 1. Okay? And the book said you like get the first point of difference. The first point of difference, 1 and 1 are the same, and that's the first point of difference. You have 2 and 3. Right? You want to use a small number, you don't want to use 3, you want to use 2.
Where are those numbers coming from?
They're coming from, you decide if you don't have, if there is no parent, you decide which one you're starting from. Let's see, that's what I show you. If I start with the first set, I start from fluorine. If I start from fluorine, I get 1, 3, 4. Alright? Then if you choose, is that your best choice? You see, I can start from one ethyl. If I start with one ethyl, I get 1, 2, 4. Because you can start with either one. But for this initial problem, you cannot choose what you're starting from. You have to start from this OCH3. But for this, again, you can do clockwise, counterclockwise. There are so many you have to decide, right? So you first sometimes you have to decide what you're starting from. Then if you don't have to decide that, you have to decide to go left or to go right. And then the principle is you try to get a small number. Or try to get a lower number. Lowest number is okay, any other questions? Okay. Sometimes benzene will be named as a substituent, not as the substrate. Okay. So as a substituent, benzene will be referring to as a phenyl group. That's the example of benzene as a phenyl group, right? It's not easy to sometimes to use benzene as a parent, and I don't know what time we're going to use benzene as a parent. Here, there you go, right? So how you name this? You can name this as something like this. Okay? So you choose your parent compound is this. What is this? Ethanol. Right? So this will be our parent, ethanol. Now this is not for this. So you starting from this and you see what is the difference between this ethanol and the compound name. That means on this carbon, you have a benzene ring. You have benzene ring here. Get it? And let me take that away since that's the name. Okay? So this is ethanol. Ethyl, right? So this is ethanol. And now you attach on this carbon, okay, a benzene ring. So then you will name this not simply ethanol. Ethanol has much higher priority in the naming. Somewhere I will show you this priority. The priority also depends on the oxidation state. Right. So this will be our carbon number 1 for the ethanol, but it has OH on it, and this will be our carbon number 2. So then your name becomes relatively similar. So you have 2 phenyl ethanol. There's very similar as arylic carbon. There is earlier, remember like what we talked about yesterday? Right? There is a benzyl position. What is the benzyl position? Is the carbon that attached to the benzene ring right away. Okay? So this is the so-called, let's say this is C. And this will be the benzyl or benzylic carbon. And if you put something on this carbon, for example, you put a Br on it, and you still have 2H on this. Okay? And this compound become benzyl bromide. Similarly, if you have some other group attached to benzylic carbon, right? You will call this benzyl alcohol. Okay, so then the biphenyl is accepted IUPAC name for a compound with two benzene rings connected by a single bond. And then the naming has those kind of convention. So you start for each one ring, benzene ring, you start at the bridge. Okay, so you name them 1, 2, 3, 4, 5, 6, as we saw here. Okay. On which side you use a prime nomenclature. You can use the prime numbers on right or on left. Okay. For example, if you have a biphenyl molecule with some of those salts treated in the on8, like this, C83 Cl. Okay. And according to the number 16, you will call this 2